All right, so could you lower the light level as much as we can? Very dark. I want to be very dark. All right, thank you so much for coming out on Saturday. And this is my first Saturday lecture, and I don't know how I'm going to do. But my name is Shim. I'm from Arizona State University. I'm a faculty member there. I'm going to talk about pressure, temperature, volume equation of state today on Saturday after going through 5 days of intense, workshop schedules, 1.5 hour talks, 4 times a day. I'm pretty sure that you have full of energy, but if you're like me, and my energy level is a little low today, but I'd like to focus on one topic today rather than covering a lot of grounds. And I want you to use equation of state as a very useful tool, but also in an informed way. Okay, there are actually the things that you have to understand to be able to use appropriate way, and you also want to understand some physical background so that you can plug in the right equation to the right problem. Not all the equation of state that we are using are perfect. Actually, none of them are perfect. They are based on some assumptions that are not well known, and there are also, cautionary remarks that I'd like to make today. So, all right, so the first slide that I have is a little animation. I try not to use bright colors for the meditation purpose so that you can relax and calm down Saturday. Don't sleep though. So this is the crystal structure of bridgemanite, lower mantle mineral. And the reason that I'm showing this animation first is that you can calm down and relax first by watching it. But I'm going to show this animation a couple of different occasions during my talk when I need to have a break. I cannot go on for 1.5 hours straight. And I hope that you have some break for asking questions as well. But more importantly, I'd like you to stare at this animation a little bit. Then breathe. And think about what actually this animation tried to tell you about the equation of state. In fact, there is. So I'm going to talk about it in later part of my talk. Okay. Just for the side note, if you're not familiar with the crystal structure of bridgemanite, this little one that sits at the center of this sort of 6 different bonds is the silicon atoms surrounded by 6 different oxygen atoms. Okay, I intentionally left the magnesium out just to highlight the sort of physical or thermodynamic stuff that is going on in this animation. It's very subtle. Okay, so what is equation of state? The equation of state simply states that it's an equation of equations that relate the state variables, and I'm pretty sure you're familiar with what state variables are in thermodynamics. It's a variable that depends only on initial and final conditions, and it doesn't care about what kind of path you bring that parameter from initial conditions to the final conditions. That becomes really handy when you derive equation of state. Okay? So there are different type of equation of states out there that relates different state parameters. It's not just pressure, volume, temperature. There are others like entropy, energy, and stuff like that. In fact, there are experimental techniques that allows you to measure energy change during pressure, change or volume change, which is pretty remarkable. But my focus today is on relating pressure, volume, and temperature, which is really handy for us to use if you're concerned about Earth interior, because pressure effect is really large and temperature effect is not as big as pressure, but it is also important. And the density itself is very important in understanding dynamics. We heard a lot about density of LLSBP, and I'm pretty sure you might have a nightmare last night about LLSBP. But that is one example that I cannot really skip, bring it up because the density is so much important. But by knowing equation of state, you can also derive other useful thermodynamic parameters. Okay? It's not just about the density. Okay, so the overview or roadmap of my talk. So I'm going to talk about thermodynamic and physical background. Okay? By the way, you should interrupt me anytime that I miss something and I do poor job of defining any parameters and stuff like that. I like to encourage students and postdocs to ask questions, and also seniors to chime in if I make the wrong statement or something to add. Okay? And then I'm going to talk about different equations, 4 different equations today. And I'm going to also talk about advantages and disadvantages and different approaches that I'm going to talk about, and particularly limitations. And then I'm going to talk about applications for earth science and also a little bit of planetary science as well. So one equation of state that we learn in middle school or high school that you know really well is ideal gas law that relates pressure, volume, and temperature already. And it provides nice intuition to the problems that we're going to deal with today, which is how pressure, volume, temperatures are related to each other. So first, very intuitive, and I don't probably have to explain to you about why this is the case. Volume increases with temperature. Yeah, thermal expansion. You know that. Volume decreases with pressure. Yeah, materials are compressible, so you squeeze things and they accommodate the stress by reducing the volume. How about this one? Pressure increases with temperature. Make sense? Or Saturday morning, low energy, no response. Okay, well, this statement is not complete. What do we need to complete this sentence? For fixed volume, right? So if you have a box that doesn't expand, somehow it resists to expand with heating. So you increase temperature, you have particles inside, like gas particles, atoms, or molecules, whatever you want. And then they oscillate with heating or temperature increase. And then if you don't allow volume to increase, what happens is that those vibrations translate into pressure increase. Okay? So these are 3 things that I like you to remember when we derive equation of state, because our equation of state needs to make sense. Okay? We heard a lot about stress-strain relations last 5 days in seismology talk given by Steve Grant, and also fluid mechanics and others. Okay, so stress and strain are second-rank tensors. They have 2 subscripts. And there's a material parameter that relates stress and strain, which is single crystal elastic constant, so-called CIJKL, which has 4 subscripts, which means that it's 4th-rank tensor. So it's a nightmare to deal with this problem if you want to have global modeling. Fortunately for today, equation of state. I'm going to get rid of all this. I'm not going to talk about it. But it is important to still remember that crystal systems that we deal with has an anisotropy. The second important thing, or it's probably more important than the statement that I made, is that in this equation, we are making an assumption between stress and strain. What is it? Linear relationship. Does it hold for the Earth interior, where the pressure increases quite a lot? Okay? It turns out, and you probably know the answer already, is that this linear relationship does not hold anymore if you worry about the size of planet like Earth. Okay? So this is a volume pressure relations of bridgemanite in the mantle. Lower mantle start at around 25 GPa, and the core mantle boundary is about 135 GPa. And the volume is normalized to the volume at reference state. In this case, it's a volume at 300 K and 1 bar, so room pressure and room temperature conditions. And that's obviously 1 at the corner when you have no pressure. And when you increase pressure, obviously volume decreases, but you realize that it doesn't decrease linearly. It has a curvature. It has a curvature that actually tells you something about how the compressibility changes with pressure as well, right? So the compressibility increases, or decreases, I should say. Yes, Saturday, with pressure. So as you go higher and higher pressure, material becomes stiffer and stiffer, and that explains why you have this curvature, okay? So you cannot use that linear relationship anymore.
Dan,
yeah, sure.
I thought bridgemanite was only a high pressure phase to start with. So what does it mean when you plot these curves down to lower pressures? Good
question. So there's a term that we use in thermodynamics to describe that phenomena, metastability, right? A diamond is not forever. And that's a pure lie, okay? Well, it's nearly forever because it's metastable at 1 bar, which means that the stable form of carbon at 1 bar and 300 K is graphite, right? There are actually materials that has a huge kinetic barrier, the barrier that you have to overcome to transform something into the stable form. And bridgemanite does not have insurmountable kinetic barrier, but it does have kinetic barrier. So it's not really easy to break down the bridgemanite at 1 bar and low temperature. Yet with moderate heating, you can easily break down the bridgemanite at 1 bar. And mineral physicists have a history of learning that process in early days. So yes, it's an important problem. And it's particularly a problem for calcium silicate perovskite, which turns into glass when you release pressure. So you cannot measure actually 1 bar volume, okay? So there are cases that we have to really worry about extrapolating the equation of state back to the regime where minerals are not stable. And that's a common mistake we sometimes make. But in this case, it's not a mistake because it's metastable, okay? If metastability is severe and it starts showing anomalies in pressure, temperature, pressure volume behavior, so you should take those data out to fit reasonably well because it's a volume pressure relationship during instability or become more unstable with release in pressure. Okay, so the amount of strain we're going to deal with today in the Saturday morning is 20 to 30% for the mantle, okay? That's not so much, but it is large enough that you cannot use linear relationship. That's the point. Okay, so the parametrical space that we are going to explore today is pressure, volume, temperature. So let me show you where they are. This is a pressure increasing this way, and temperature increasing toward the inside, away from you, and the strain or volume change or normalized volume increasing vertically. And now you see a plane. Okay, this plane is an equation of state. Okay, in pressure, volume, temperature space. Now you can recognize that it has a slope and it's curved, right? It cannot be flat or vertical, right? If it is flat or vertical, it means that one of the 3 parameters are useless, right? Constant. So it does have a slope. It turns out that the slope and curvature are all very sensitive to, in fact, the material properties. This particular plot is made from the material properties of bridgemanite. And I'm going to go back to this slide just to relate the physical parameters to the shape and curvature of this plane. And that actually hopefully helps you to remember equation of state better.
Where is the color?
Oh, the color means nothing. It's just for the illumination. It just show that yeah, right. I'm sorry. Yeah. So we start everything starts from energy in thermodynamics. So understanding the equations that describe energy gives you a way to derive all the equation of state we will see later on. So there are 4 different definition of free energy that I'm showing to you today. Don't have to memorize. Do you remember what this is? Internal energy. Helmholtz free energy, Gibbs free energy. It turns out that for equation of state, the most useful energy definition, free energy definition, are the internal energy and Helmholtz free energy. And just to give you the answer right away, the internal energy is related to the adiabat, and Helmholtz free energy is related to isotherm. Okay? For the experiment and some of the density functional theory, it's easier to deal with isothermal situations. But for planets, yeah, we don't have isothermal situation as a function of depths and likely adiabat. So this becomes very handy when you deal with the planetary interior situation. So now, a few terms to remember. Okay, am I going too easy? Right? Yeah, I'm sorry for those who are offended by being too easy. Isothermal, right? You know what it is. Isobaric. Yeah? Isochoric. Yeah? Can I skip? No. Constant volume. Yes. Isentropic. Entropy. Yes, that's close actually. And adiabatic, right? Constant heat. So these become really handy when you derive equation of state because you take a one parameter, a knowing parameter out of the way and you don't have to worry about it. Okay? So I'm going to bring these terms back and back again during this talk. Okay, so energy. So now I'm showing that definition back again. And the key thing to remember is that internal energy is related to the variation in entropy and volume. Entropy, by the way, is a very difficult parameter to measure in the lab. Maybe not the case for density functional theory. If there's an expert out there, you can probably chime in. Helmholtz free energy is related to temperature change and volume change. Gibbs free energy sounds like, wow, that sounds logical definition to use because it is related to temperature change and pressure change, which actually our intuition, the way our intuition has been developed, because we normally think of volume as a dependent variable and pressure and temperature as a controlled variable or independent variable, right? But the way that we're going to derive equation of state is a little counterintuitive in a sense that we put pressure as a dependent variable and use volume and temperature as an independent variable, okay? So what that means is that we are not going to use this one, but rather we're going to use this one and this one. Again, reminds you this is related to adiabatic. This is related to isothermal. And that already gives you how we're going to derive equation of state, because for isothermal, okay, dt goes 0, nice, convenient. And for isentrope, goes to 0, and nice and easy. And if you actually look at the way you rearrange the term, there's a nice equation that you can see that the pressure is related to the partial derivative of free energy with respect to volume change. Okay? So, well, and then there are 2 definitions that you can see, or relations, I should say. You can see is that the subscript here means the constant variable, which means that the pressure is literally the free energy change as a function of volume for constant entropy situation, which means that if you take internal energy and then measure the volume sensitive change, then you will get adiabatic pressure change. Nice. Okay? The second one tells you about the adiabatic pressure change as a function of volume change. Okay? So you already have equation of state here. So I can finish. Now, there are actually key 3 thermodynamic parameters that I like to refresh your memory for, because they actually already are relating pressure, volume, temperature. Okay? So, isothermal bulk modulus. So it's sort of like an incompressibility. So how difficult material how difficult it is to compress the material. Okay? So it is defined as a partial derivative of pressure with respect to volume for constant temperature. If you wish, you can change the subscript to entropy, then you get adiabatic bulk modulus. Okay? And from this equation, you can already realize that by knowing the bulk modulus of a material, you can relate pressure and volume. Right? And it also tells you that this material parameter is actually indeed related to the free energy of the material, too. There's a second derivative. Okay? So now the second parameter that I'd like to refresh your memory for is a thermal expansion parameter, which is defined to be the partial derivative of volume with respect to the change in temperature for constant pressure conditions. So how to convert temperature into volume effect. That's a different way to describe this parameter. Now, the Grunheisen parameter. You heard about this Grunheisen parameter many times last 5 days. It finally appears with more clear definition here. Unfortunately, Grunheisen parameter has been defined perhaps 20 or 30 different ways out there. But to me, this is the most fundamental definition of Grunheisen parameter. And in fact, you can see almost 20 different names of Grunheisen parameter. There's a mode Grunheisen parameter, thermodynamic Grunheisen parameter, elastic Grunheisen parameter, stuff like that. So don't worry. It boils down to this definition, to me at least. Okay, so in equation of state, the reason that Grunheisen parameter is really important is that it allows you to convert temperature effect or thermal effect into pressure effect for constant volume case. Okay? So this is the least intuitive of the 3 statements we talked about in ideal gas law. Right? Do you remember that? Okay. Any questions so far? Yeah.
What's that
CV, it is a heat capacity for constant volume. Yes. Good question. Sorry. See, I don't define the terms. Yeah.
Mostly in upper mantle, most of the rules of chemistry we deal with CP.
Yes.
How do you measure CV on a solid?
Well, CV, we have in fact, we use Grunheisen parameter to convert CP into CV.
I see.
Yeah. Sounds a little, reversed.
Circular.
Circular.
So it's not a measurable parameter, in essence.
Well, I don't want to make a mistake of saying it is not measurable, but it is probably very difficult to measure. Right. So heat capacity we normally measure at 1 bar is CP, constant pressure. Yeah. Any other questions? Yes.
It seems like you've used the terms isentropic and adiabatic almost interchangeably, or perhaps I misunderstood.
Yeah, I almost use it interchangeably.
Are they the same?
Nearly.
Okay.
Yeah. Any better answers than me?
They can be different. I mean, can you give an example how they're different?
I didn't think about it.
In your definition
Anybody?
of entropy and
Yeah.
in your definitions, they look mathematically different.
Yes, it is. Because isentrop is really fixing the entropy value the same. And so essentially the difference comes from if you can bring up an example, that example has to deal with a case where no heat exchange, still with an entropy change.
How about a shock wave? No, it's just a gas expansion in vacuum that is an adiabatic process, but it's not isotropic. It's because of the irreversibility.
Second law of thermodynamics defines reversible and irreversible processes.
Great.
Thanks,
Great.
Dan, because Frank's Spirit students take me to task on this all the time, just like Jonathan, so I have an answer.
Anybody else? What questions? All right, so we're coming back to this slide of shape of equation of state in parametric space of pressure, volume, temperature. The quiz. Bulk modulus. What aspect of this plane is sensitive to bulk modulus? Curvature and slope along, that's very important, along pressure axis, right? Or if you set up a plane that is parallel to the screen, that's constant temperature plane, right? And the curvature, or if you think about intersection between this plane and that hypothetical plane that is parallel to the screen, you'll get a curve. And the slope of the curve would be the bulk modulus, would be related to compressibility and bulk modulus. Bulk modulus is not truly inverse of the compressibility, but related to that, right? Make sense? Yeah. So it defines the slope along this direction. How about you can guess now what I'm going to ask? Thermal expansion parameter. Anybody? Yes. So, well, the fact of the matter is this plane is sloping towards you. So it slopes this way. Okay? So alpha literally describes if you sit at 40 GPa and you try to climb this plane, it describes how hard and easy that climb would be. Make sense? Right?
Because the question is, in real materials, which one's the bigger climb?
Good question. So the question was, for the real materials, which one is a bigger climb? But that depends on how much pressure change and the temperature change you're talking about, right? So in this view, it looks like at least at one bar, the climb along alpha direction seems to be more difficult. Yeah. Gruneisen parameter. This is probably the most challenging one. Anybody?
Is it the ratio of the slope?
I didn't even think about it, but you're right. Yeah. Later on, I'm going to give you a slide that relates Gruneisen parameter to alpha and KT. Okay? So product of alpha and KT gives you gamma. And that's strictly true in thermodynamics. But what gamma in this plot describes is a curvature. If you think about setting up a plane that is parallel to the PT plane, like 0.9, for example, you get intersection between this plane and the horizontal plane. Then you will get a curve, right? And the slope of that curve is related to Gruneisen parameter. Great. Right. So you master the thermodynamic, PBT equation of state. All right? So now, people actually loves to project the property. In fact, this is more common view of the PBT equation of state. So this is literally taking projection of this diagram toward this direction. So you get rid of temperature axis. So temperature axis runs this way. Instead, you plot so-called isotherms in pressure volume space. So the blue color here shows 300 K isotherm, and The dark red one is highest temperature in this plot is 4,000 Kelvin. Okay? So now you can relate that 3D diagram into this 2D diagram. Okay? All right? Good. So now, let's say that you want to figure out the pressure, volume, temperature relations at this particular point. By the way, these lines were calculated using thermodynamic parameter of Bridgmanite. Now, yes, this is the total pressure at this point, which is about 70 GPa, and the volume is 90% of 1 bar volume. And at 4,000 Kelvin, the approach that we're going to take when we derive equation of state is a little weird one, that we break down this total pressure into two different terms. We can do this because pressure and more fundamentally energy are state variables which do not care about the pathway between the initial and final conditions, right? So we can break down into the sum of so-called static pressure and thermal pressure. A nicer way to describe this approach is that, well, 300K isotherm is so much easier to measure in an experiment. You don't have to heat. You don't have to deal with that nasty thermal gradient, whatever problem you heard about the diamond cell. 300K, temperature is there always at 300K. You don't have to control. So you can measure this nicely. But then for the Earth interior, you want to add the thermal effect. The way you add the thermal effect is to maintain the same volume, constant volume. Volume doesn't change along this line. Only thing that changes is the temperature that converts into the pressure effect. Okay? Following me? Yeah. So now you can smell why Grüneisen parameter is important, right? I talked about the Grüneisen parameter being almost like conversion term from pressure temperature effect into pressure effect, right? Right? Okay, cool. So if you write down the equation based on all this argument that I made through visualization, you come up with these equations. So this is Helmholtz free energy. The total energy at certain pressure and temperature conditions can be broken down into many different terms through different contribution. Static Helmholtz free energy describes in normal case for experimentalist is 300K energy change as a function of volume change. In density functional theory, the reference state can be different, like 0K, or complete static conditions where you don't have to worry about 0-point vibration. Am I right or wrong? Yeah. So it depends. So you need to be careful about this term, okay? Reference temperature. Now, thermal effect, there are many different ones. For the silicate and ionic solid like earth materials, earth mantle materials, not the core, the thermal effect mostly comes from the vibration of atoms at different temperatures. And then for metals, there's an electronic effect that we don't know very well. Okay? For certain cases, you don't have to worry about it. For earth mantle, silicate, and oxide, seems that it doesn't really matter much. For iron, I don't know, but my intuition is that the effect might be pretty small. Probably smaller than the error bar we normally have, but I could be wrong. And if you take the first derivative, partial derivative of this equation with respect to volume, if you remember that thermodynamic relations, you come up with pressure relations, right? So this relation directly comes from this relation by just taking partial derivative of this one with respect to volume. If you take constant entropy, then you will get adiabatic equation of state. If you take constant temperature, you get isothermal.
I think it's worth to mention that the thermal part, especially if you take the electron out, it solely comes from the asymmetry in the interaction potential of atoms.
Not solely. It could come from the asymmetry of the interatomic potential function, particularly if you go very near to the melting point. But fortunately, bridgemanite has really high melting point, way above the geotherm, right? So that enharmonic term normally assumes to be small, that you don't have to worry about. Yes, that's a good point. I'm actually deriving all this equation under the assumption of harmonic oscillation behavior, which I don't get to describe yet, because I'm not getting into the thermal part yet.
Because I think if the potential, well, for the interaction of atom is perfectly harmonic, then you would not have Grunitzen parameter. The Grunitzen parameter is an outcome of the aharmonicity of the potential.
Yep, that's true. That's true.
So you cannot derive, like, say, thermal expansion if you don't have aharmonicity.
Well, the enharmonicity, the equation of state, in the end, you will see by the end of the talk, has a built-in way to compromise that weakness through so-called quasi-enharmonicity. So you are shifting the curves to fiddle into that asymmetry. But I am not prepared for talking about that because I thought it's a little more advanced topic than I want to talk about today. But that's a very important point. Yes?
Yes, also in the case of solid solutions, you have a term of configurational free energy coming from the configurational entropy.
Right. So the equation of state that I'm describing here is valid for fixed composition without phase transformation. It's a relation that describes the pressure, volume, temperature in a stability field of one mineral in fixed composition. That's what I'm aiming here.
Yes, but even with a fixed composition, you can have several sites.
Order disorder.
Yes.
Yes, then you need additional term. Yeah. Thank you. So, let me look at the history of this argument a little bit. We learn from somebody else's mistake. It's not necessarily a mistake. It's all they can do at that era because of the availability of the data and with their error bars and all that stuff. So, the simple form of static equation of state you can develop is through using the definition of bulk modulus, okay, which relates the pressure and volume. So now if you assume that K is constant and you integrate this equation, then you come up with this very simple equation of state that relates pressure with volume, and V0 is measurable at 1 bar, K0 is measurable, bulk modulus at 1 bar, measurable at 1 bar. So it's convenient. But the assumption is that the K, bulk modulus, doesn't change with pressure. From intuition, we know that is not true because as you increase pressure, material gets stiffer and stiffer. So the second compromise that you can make is to write the equation in a way that you accommodate the pressure-dependent change in bulk modulus. So this is bulk modulus and any arbitrary pressure conditions. And this is bulk modulus at 1 bar. And this is linear assumption. This is pressure derivative of bulk modulus, K prime. Now, you can integrate and derive the equation of state this way. Nice. And we also know that this doesn't work. It's not, the bulk modulus increases with pressure, but not linearly. Okay? So, by the time Birch figure out the equation of state, now that becomes famous Birch-Monahan equation of state, he had enough data and with sufficient precision and accuracy to develop very high, quality semi-empirical equation of state. I wouldn't dump Birch's equation of state into empirical category. It's semi-empirical. It has a theoretical background as well. Okay? I'm not going to talk about it, but if you look at some textbooks like Poirier's book, there's a link. There's a nice description about why this is actually semi-theoretical in a certain sense. So now, well, but the way I would describe sounds like it's entirely empirical, but I want to attach that cautionary remark there. So this is energy change. It could be internal energy or free energy, any form. Is related to the Eulerian strain, which is little f. And you can see Taylor expansion of it. Yeah, if you don't have enough information, right? This is the first step to do. Okay? And Eulerian strain is defined this way and related to volume at 1 bar and volume at any arbitrary high pressure. Why Birch came up with this definition, and I cannot cover that today, but you can find that nicely in 1978 paper there. Okay? And why it is not Lagrangian? Well, there are reasons. Okay? The reason is, in some sense, pretty simple. Didn't work. Yeah, that gives you a sense that this is, somewhat empirical. So now, there's a problem if you do this way, right? What's the problem?
If f goes above 1.
Or if f doesn't, well, higher order term of f is not sufficiently small, right? It matters where you make truncation, right? That's really important. So don't make extrapolation. That's my first message. Okay? So if you have a data that covers up to 60 GPa, stop there. Anything you do above 60 GPa, you're taking a risk.
So that should be always smaller than.
No. Well, we'll talk about it later. I'll show a slide later. Yeah. So now, second order Birch-Monheim equation. Well, it's simple. You truncate it after second term, and you then do the simple math until you figure out ABCs and their relationship with physical parameter that we know for boundary conditions that we know. For example, at 1 bar, stress energy goes to 0. At 1 bar, bulk modulus notation is K naught. And if you do that, you can get this equation of state. It's the second order. The two variables, material-dependent variables that we are talking about is volume at 1 bar and bulk modulus at 1 bar. Okay? Very simple. For most of the lower mantle minerals, you can measure these two parameters in the lab, and then you can just calculate the pressure as a function of volume nicely.
When you extrapolate, what is worse, the equation of state or the parameters that go into it?
It's an equation of state that start predicting something not really right. Yeah. Well, it depends, because K naught and V naught is a measurement at 1 bar anyway, right? So if you go beyond where the data point exists, so you rely on these assumptions. Okay? So now, the nice thing about this equation is that if you take the volume partial derivative with respect to volume, then you get bulk modulus as a function of volume at high pressure, which means that you can calculate bulk modulus at any given volume or pressure. That allows you to calculate bulk sound speed, right? And that's how Burnman works. So we had a nice introduction on Tuesday about Burnman, but when you use it, you probably want to read a little bit about what you're dealing with, right? Not everything is perfect. Third order equation of state. Okay. So now the truncation happens at one higher term, and now you get more complicated equation of state, and now you have 3 parameters to fit to or concern about. Volume at 1 bar, bulk modulus at 1 bar, and pressure derivative at 1 bar. Okay? how fast or slow the bulk modulus increases with pressure. In fact, if you look at this equation, you'll probably realize a nice aspect of these relations between third and second order. If you plug in 4, it turns into the second order, right? Because this goes to 0, this term goes 0, and this is the only term that survives. That's essentially second order equation of state. What that means is that if you truncate the term higher than third order in second order Birch-Monheim equation, you're not ignoring K prime. You are actually assuming K prime equals 4, right? That's a little spooky, right? You don't do something you don't intend to do because of the way the equation is developed. Now, you can go on for the fourth and fifth, whatever order you want to do, then the terms that you have to worry about, the number of terms that you have to worry about increases. Now, the truncation problem is a real problem.
When you go to fourth order,
yes,
do the higher derivatives of K come into play, like K double prime?
That's what I'm going to talk about on this slide. Thank you.
Sorry.
So, no. I'm glad that this type of question actually makes me really happy because you're following me, right? You're following the logic. So that's really great. So, cool.
One more question.
Yeah, sure.
So is it true that for most silicate material, K0 prime is close to 4? So the K prime 0.
Yeah.
So in that sense, the third order and second order are almost the same.
Yes.
For the silicate material.
Yes. But there are people who don't know much about this history, and they ended up using K prime equals 4 for example, very soft materials like ice. Okay? So you know, that brings you an interesting question that you want to know a little bit about what's in the background and assumptions as well. Yeah.
Dan, is it simple to understand how we go from that Taylor series to getting an exponent of 3/2?
I'm sorry, exponent of?
Well, we have very nice series, and then we have exponents that are 3/2.
Oh, yeah, that's because of the relationship. I don't know whether I answered you correct, but that's the relationship of this one. Little f and the strain is related to exponent.
The definition of strain, which is little f, comes from using a finite strain rather than an infinitesimal strain, so keeping the cross terms, and then defining in a Eulerian reference state rather than a Lagrangian reference state.
Yeah.
So that's the Moynihan contribution.
So the first two slides that I showed for the failed attempts, they tried directly to relate to the volume ratio into pressure. And that turns out to be unsuccessful. But later, the second equation of state that I'm going to show you directly related the length scale into the pressure. So more intuitive in some sense. Okay. So
one more question.
Yeah.
Does that apply to liquid?
Can I answer that question later part of my talk?
Okay.
Yeah.
Sorry, this is just an answer. There's also a partial derivative with almost energy with the chain rule that results in those 7/3. And so, there's a partial derivative. And that's why, it's not particularly hard. It's just a lot of, algebra to get between.
Any other questions? Yeah.
Is there an intuitive reason? So K prime is the pressure derivative
of bulk modulus.
Of the bulk modulus. Is there an intuitive reason why the sort of standard value, I guess, or low pressure value is 4 and not 0?
Well, people come up with their own intuitive reasonings of why silicate and oxide has K prime equals very close to 4. Is that what you're asking?
I think, yeah.
Yeah. I don't think I know the answer.
Why is 0 not a more intuitive?
But, these solids that we deal with for the mantle we call them ionic, okay? Which means that, if you think about your Chemistry 101, we talked about 4 different bond types: covalent, ionic, metallic, and van der Waals, right? And the ones that comes out very close to 4 happens to be all ionic bond. So people love to connect that into a mantle silicate being more ionic. And people believe that as you increase the pressure, the character of the bond in these crystals become more ionic and ionic. So that's why it comes out 4. But I don't know whether theorists have ever explored these questions in density functional theory, whether there's any relationship.
Just a quick comment, which is in parallel to Dan's statement, which is if you substitute K prime equals 4, you find that that's just the second order Birch-Moynihan equation of state. So you truncate that third order term with a K prime equals 4. So that just comes out of the algebra. Right. And so the fact that for lots of oxides and silicates and metals at Earth, at deep planet conditions, have K primes close to 4 is a way of telling you that the expansion around this strain is probably a good expansion because the higher order terms start going to 0 rapidly.
Excellent point. Yeah. Okay, can I move on? I suddenly realized that I have to move pretty quickly to be able to finish the ones that I like to talk about. Okay, so now the problems. This is fairly important. So higher order terms are not necessarily small. Think about this. If you go to extremely high pressure, your volume at high pressure is much smaller than volume at 1 bar, right? And this term goes really large with pressure. With the increase of pressure, this becomes large, which means that this will be large too, little f. So instead of higher order term being smaller and smaller with pressure, in fact, they become larger and larger. All right? So that makes extrapolation of your equation of state beyond the point where you have a data. It's a pretty scary one, but people are doing it in other community.
So as we get more and more precise measurements at high pressure, say at 20 gigapascals, would it not make sense to have the reference state, use that as a reference state rather than ambient conditions?
Yes, there is an attempt for that too. So yes, Barbara made a great point that the V naught or K naught, the notation of subscript naught, is arbitrary. You can actually set, for example, 20 GPa as your reference point. That becomes really handy and important for the crystals and mineral phases that becomes very unstable out of their stability field. Good example is calcium silicate perovskite. Yes. So the formalism has been already developed in 1984 by Heinz and John Lowe. So people have used it for Birch-Moynihan equation already. Yeah. But there are also other problems because error bar tends to be very large at that conditions. Well, it's getting better. It's getting smaller. But it's still larger than the error bar you can get at V naught. So the whole curve suffers from initial condition being more or less uncertain if you take that approach in certain cases. Yeah. So the second problem that I want to emphasize, not a second problem. Yeah, well, not a problem, but something that you have to remind yourself is the second order Birch-Moynihan equation of state assumes K prime equals 4. And what about the higher order equation of state? Yes, it's not just simply some parameter being some value. If you go to third, fourth order, it becomes nastier and nastier that these 3 parameters, for example, are related to each other, which we don't want. But it is because of the downside of the Taylor expansion. So now I'm going to move toward the more modernized equation of state by Vinay et al. So now the idea, what Vinay developed is a very simple but theoretically sound approach where he used actually thermodynamic notion of free energy related to temperature and volume change, particularly volume change. Okay, you take this out, And now, what this equation tells you is that if you know the functional form of free energy as a function of volume, then you should have equation of state, theoretical equation of state, right? The problem is, well, what this one tells you about is, one of the audience mentioned about pair potential. If you have a cation and an anion, you have a Coulombic attraction between them. So if you bring them close, the energy goes down, right? Like my voice. And if you actually bring them too close, both cation and anion have electrons. So you start having problem with a repulsion between electrons in cation and anion that brings up the energy high if you bring them too close, right? We want to have our own space. If someone goes into our space, we feel a little agitated, right? And that brings our energy level a little up. Same for the atoms, right? So if you have a good functional form that describes the physics of this pair potential, then you can plug into this equation and you can get the equation of state. And that's exactly what Vinay did. So he surveyed a suite of materials from silicate, oxide, gas, and even the surface absorbed ionic species. And he normalized with certain parameters, energy and distance, and scale it, and he find that all the data from a variety of different materials magically fall into this relationship that resembles the pair potential quite nicely. But by fitting this data into a curve like this, he was able to get energy being described as a function of sort of like scale distance between atoms. Okay, and then he took the first derivative with respect to volume and get this equation of state. Yes?
Is there any reason to think the nature of the bonding changes with pressure to become, for example, more covalent and less ionic?
No, it becomes more ionic than and less covalent. Yeah, it becomes more like ideal in some sense at low temperature. But high temperature brings in other characters too, back into the picture too. Yeah, but I don't know particularly how that can be explained by, modeling the electron structure more correct way, which is quantum mechanics. I don't know. I mean, ionic and covalent is pretty empirical description of bonding in some sense, right? No electron is truly not shared or exchanged in any of those density functional features.
Yeah, particularly in the silicates, which sort of hybrid. So I'm wondering, they might, the extent that it's one or another might change with pressure.
Right. Well, it's very difficult to make a good measurements on how much is covalent and how much is silicate at high pressure. There are methods at 1 bar, but those methods requires very high quality measurements of electron density. Okay, I promised the time to meditation, but unfortunately I cannot do it because I'm running out of time. But so this is the Vinay equation of state. The nice thing about Vinay equation of state is that you don't have to deal with truncation. It's exact. Okay, there's nothing hidden, and it's a 3-parameter equation of state: V naught, K naught, and K prime. Okay. Volume at reference conditions, bulk modulus at reference conditions. What is the third? Pressure derivative of bulk modulus at reference conditions. We need a break, right? So now, real data. I'm showing a real data measured in the lab. 300K, high pressure. So this is silicon carbide. No, it's not earth materials. Okay, but it's an example that I want to show that you can measure a bunch of data points at high pressure and measure the unit cell volume. Then you fit into the equation of state. The curve behind shows you, and there's a fit residue after fitting, and it's within the 1 GPa range, which is okay. Okay, so this is how you get the equation of state fitting, and out of this fitting, you can get V naught, K naught, and K prime, right? Then you can use this equation to describe any pressure in between 0 and 60 GPa. If you want to have some risk and adventure, you can go beyond 60 GPa. Now, in this approach, you fit 3 parameters. But there is a caveat. What is this? This is a contour diagram. X-axis shows K0. Now, this is from the real data I show you on silicon carbide. V0 is very well known, so you don't have to worry about it. You fix it to the known value, so you don't have to fit. In this fitting that I showed before, we only vary K0 and K prime for Vinay equation of state. Okay? Now, the contour here shows the chi-square, so fit residue, right? So in normal regression, you run regression until you get lowest possible chi-square, right? So if you look at the contour, yeah, it's decreasing toward this direction, but what do you learn from this diagram? They are related to each other, K and K prime. They are negatively correlated. So fact of the matter is, any pair of values you take along this line will be equally okay. And that's a pretty scary message, that there is a correlation between them. So the typical way to approach this problem for mineral physicists is to constrain, for example, K0 from other experimental values like direct elasticity measurements. Then you have known value for this, and then fix it, and then you get this one. Okay? So that's the approach. So unlike what you saw, smaller number of variables you fit, it is normally better. Right? That's probably also true for other types of regression and fittings as well.
But Dan, for the rest of us, does it really matter in the end? If there's a
trade-off
between those parameters?
Yes. Well, the trade-off between the parameters really matters, because if you look at some tables, which value to use, right? If you see negative correlation from pair of values from 2 different groups, you think that, oh, they are really different. But they may not be necessarily different in terms of real data. They might be exactly the same, but just trade-off gives you a different pair of values. Yeah? Yes. Normally these days, the question was whether data is available in the publication these days. Yes. So go to supplementary information. Download the supplementary information, there should be. Then you can play with the fitting. So if you look at the mineral physics paper, equation of state, and now this is the type of table that you're going to get. Now, let's look at gold. Okay, this is V0. Okay, fine. KT, well, K0, bulk modulus, pressure derivative of bulk modulus, that's fine. You have, again, bulk modulus reappearing, pressure derivative of bulk modulus reappearing. Don't worry about the last 3. Why is that? And they are slightly different, right? What this tries to tell you is that for exact same data, same numbers, if you fit into the Birch-Monahan and Vinay equation of state, you still get little different values. They don't give you the same fitting parameters because their formalism is a little different. The message that I try to send you here is that if you took a value from a paper that the data was fitted to the Vinay equation of state, and then you plug into the Birch-Monahan equation of state, don't blame the authors if you get different numbers. It's not their fault. It's your fault not reading the fine print well.
Hey Dan, can you give us some guidance, either theoretical or some kind of a heuristic for which equation of state one would choose to use? Here you show both, but is one more appropriate for some
Let me go through
material?
this, and then I'm collecting this questions that can be answered better after the talk. Yeah, but that's really important thing. Okay, so 2 questions. So now I can take some break, but it's probably too late because you want to take it? No. I want to finish my part, but questions? Or you want to watch this and take some meditation? Yeah. Yeah, go ahead.
So if you do have
You can actually easily convert it.
Can you repeat that question?
You can just convert the number, okay? That's the best way. Yeah. You just have to solve the equation. That's it. Yeah. That's probably best. And then for someone who do modeling, I would probably suggest you to clearly cite the paper that you use the equation of state data from and the equation of state that you're using from for the reproducibility by others.
It seems to me that if you extrapolate the Van 't equation of state to very high pressure, the asymptotic behavior is off from the Thomas Fermi-Dirac.
I'm sorry?
It's off from the Thomas Fermi-Dirac equation of state that you could derive.
So that brings up a very important questions. There's no such thing universal equation of state. What do you mean? There's no equation of state that can be universally applied to any different state of matter. Some equation of state are optimized for solid. Some equation of states are optimized for liquid. Some equation of states are optimized for plasma. Don't mix up the equation of state.
Yeah, so it...
Oh yeah, I left it out. I'm sorry.
So what would you recommend?
In fact, I'm glad that there are people who watch this animation. I'm sorry.
So what would you recommend for somebody who's doing numerical modeling, right? Okay, I've got tons of data out there. I've got tons of people who fit equations of states, and now they've reported their parameters. Okay, will I go in, take those parameters, and say that's the uncertainty on the equation of states, or would you recommend just collapse all the data into one and try to universally?
No, as long as you mention it, you'll be fine. I'll talk about those type of issues later on. Okay, so now let's move on to the thermal part. Okay, the static part takes me more than an hour. And I thought it would be just 30 minutes, but okay. I enjoyed library discussions this morning, despite that we are doing it on Saturday. So now we are going back to drawing board, and now our job is to fulfill the description on thermal part, right? Thermal pressure. Now Gruneisen parameter is coming back into the picture. Now I'm showing how Gruneisen parameter is related to isothermal bulk modulus and thermal expansion parameters. So I'm showing you the definition again, just to remind you what they are. And then if you take the product of them, alpha kt, I'm sorry, Gruneisen parameter is not showing up exclusively yet, so don't forget about it. But what this product tells you is that if you take a product of those, you get a partial derivative that can be used for converting thermal effect into the pressure effect. That's exactly what we want for this part, right? For fixed volume, right? So now you have this handy relations. This is true in thermodynamics. There's no assumption behind it. Now, ideally, if you take integral of this term over temperature, then you can get directly thermal pressure. Then your job is completed. The reality is not that simple. We don't know how this is related to temperature in exact form of equation. We don't know this, how this is related to, for example, pressure, because alpha changes with pressure as well. So it depends on where you are in that PT space or PV space. These terms would be different. But there's a rescue that people found in 80s, and it was fine in 80s and 90s literature, but don't do it anymore. But nevertheless, I'll tell you what it is that if you think about this, let's think about temperature effect, for example. If you heat it up, the material softens. So this value goes down, K prime. If temperature goes up, alpha goes up, right? So this one goes down, this one goes up. They could offset each other. Oh, nice. So I will assume them a constant, and then use 1 bar value of alpha and 1 bar value of KT, which works pretty fine until early 90s. But once you have better resolution and precision, now you start discovering that that assumption is not actually good enough. So there's a more rigorous approach, which is so-called Debye approach that is implemented in Burnman. So, well, it takes probably an hour to go through the assumptions and all that. But simply put, what it assumes is that the crystal can be described as a collection of vibrating atoms. Okay? They vibrate different frequencies and all that. Okay? And then you statistically, throw them into the density of state and, count the, different oscillators with different frequency, and you normalize it, and you throw into the energy equation, and you get the vibrational energy. So that's how it works for the Debye model. There are assumptions, but I'm not going to go through it. But now the Gruneisen parameter is reappearing. Here the Gruneisen parameter is defined a little differently. I don't want to confuse you, but I have to. It's just that the Gruneisen parameter here is a conversion factor from energy to pressure. Okay? So you have energy of individual oscillator that you are studying in a crystal, and then you have a Gruneisen parameter for that particular vibrational mode. I know, sigh, right? Then you can sum over it, and then you get entire energy of the vibrational energy, which is almost impossible for us experimentalists to do. So we make assumption. Gamma is constant. It's not sensitive to the particular vibrational mode. So we take it out and we sum over the energy. And that energy function has some forms that are assumed based on some physical picture by Debye. And that leads you to calculate thermal pressure. Okay? The terms that I skip over, but the definition becomes important, is Gruneisen parameter. Gruneisen parameter, unfortunately, is a function of volume. So if you change the volume of crystal, the Gruneisen parameter responds to that change. So this is ad hoc empirical relationship between Gruneisen parameter and volume. This is not theoretical. And Q is not a theoretical parameter, although you can derive some theoretical relations with some other parameters, but it's not entirely theoretical. So this is more or less empirical. There are a lot of debates about whether this is correct equation to use or not. In fact, this is not correct if you go to very high pressure. This is how Debye temperature changes as a function of volume, or Gruneisen parameter, which describes which temperature the system becomes saturated or vibrator becomes saturated. Okay? We already talked about it. And then this is the formalism that Debye developed to calculate the energy. So this is a full equation you need. You plug in the number and you can get the thermal energy, thermal pressure. The parameters which are dependent on the minerals and materials are Q, theta 0, and gamma 0. Those are the three parameters of this particular formalism. Okay? The equation of states with thermal parts that requires more than 3. Okay? Depends on the approach. I'm showing you one approach today, but there are 4 or 5 different approaches popular now. N. X or N. N. Bottom equation. N, number of atoms. So this is just a conversion factor from. Yeah, it's a sort of a conversion factor for. No. N is a number of atoms in chemical formula. Yeah. So now, if you have, finally you have static and thermal parts all together in one equation. You have 6 parameters to deal with. And the message that I talked about a few slides ago is that lesser the better, right? And if you have known values, don't try to fit them, fix them, okay? And if you find a literature, a paper that try to fit all 6 parameters together, don't use it, even if it is mine. Okay? If there's another paper that fixes to the value that is well known, that's probably more likely to be right. But V naught is normally known. K naught now we can measure using spectroscopy method at 1 bar pretty accurately. So, and K naught is still challenging, so this is normal parameter that you would see in the equation of state paper that deals with this one. And gamma 0 is fairly well known at 1 bar. Q is not well known. This is normally the parameter that we fit. The Debye parameter happens to be extremely uninfluential to the outcome you get. So if you're wrong by 10% in Debye temperature, it still doesn't give you a very bad error. So we don't concern too much about Debye temperature. Although, there are other fields where that Debye temperature becomes really important. So now this is the real data that you're seeing. Silicon carbide. Color that you see is related to the temperature. So the bluer color is lower temperature, and redder colors are related to higher temperature. There's no compositional effect here. It's purely thermal, unlike tomography. And the lines here is color-coded by the temperature as well. So this is a fit residue. Yes, you see like plus minus 2 GPa. Yeah, it's more difficult, thermal effect. Okay, so we have gone through equation of state so far, and I left with 15 minutes. So little time for applications, but few things that I want to talk about is that this is not the end of equation of state. If you start taking a partial derivative of equation of state, what is handy about equation of state is that you can calculate a set of thermodynamic parameters at arbitrary pressure temperature conditions by taking the derivative of the equation of state. The examples are K, bulk modulus at any given pressure temperature conditions within the stability field of materials that allows you to calculate bulk sound speed. Thermal expansion at any given pressure and temperature. That is very important for dynamics, for example, right? If you have a material that has high thermal expansion parameter at certain depth than the other ones, right? That material would respond to the temperature much more quickly in terms of density, and then it will become more buoyant, right? So that allows you to calculate those type of things. But there are also other physical parameters. Yeah, partial derivative, sometimes it isn't really intuitive in first look, but if you think about those, they are pretty important. So we came back this one. Is that the end? Could you see that this atoms, oxygen and silicon, is actually jiggling, vibrating? Yeah. So that's the thermal part that I was talking about. Not near the melting temperature. Yes, at melting temperature they would vibrate more violently. This is probably far below the melting temperature. Okay, so now applications. Lower mantle minerals. Well, I don't talk about upper mantle minerals. Nowadays, at upper mantle pressure temperature conditions has become a lot easier to access, and we have direct pressure temperature density measurements of a bunch of minerals. And then upper mantle minerals have a lot smaller pressure interval for the stability field. So you don't get to use equation of state a lot. In fact, the lower mantle is probably the region where the equation of state, thermal equation of state becomes really handy because perovskite has unusually large pressure interval of stability, right? It's like as much as 100 GPa. This is really unusual. I don't know whether you thought about it, but think about ringwoodite, think about wasleyite, think about olivine. They're stable only for 10 GPa or less. This is resilient, remarkable crystal structure that's stable over a lot of interval of pressure, big pressure interval. So now the equation of state is really important for the lower mantle minerals. So I'm showing the numbers there, range of numbers. I don't want to offend anyone, so I want to lump numbers together and show very rough values. But two messages that I'd like to give it to you, which could be my personal biased view, but based on the literature, is that the density and elasticity or compressibility of pyrrolite seems to agree reasonably well with those of pyrolytic or PREM model. So pyrrolite is still good. We occasionally hear something. It's remarkable that pyrrolite has survived throughout all those years with a lot of different results. But maybe tomorrow we'll see a new science paper that claims that pyrrolite doesn't work. But so far it's fine. Second one, density of morph, all the results so far shows that the density must be 2 to 3% higher than pyrrolite. Really robust. Okay? Now, then pyrrolite is fine. Is that really true? The fact of the matter is there are other things that you have to worry about, and I'm going to show you those scary things too. So now, this is pretty old now, like me. This is 660. We heard a lot about viscosity jump at 660. That is probably related to post-Spinel transformation from ringwoodite to perovskite or bridgmanite and ferropericlase. Good. It's been proposed since 1932. Can you imagine? It was originally proposed in 1932, and it has still survived until 1996, where we have a first synchrotron in situ measurement of the boundary that shows post-Spinel transformation here and 660 here. Right? The message is simple. It may not be the post-Spinel transformation. Then we study their experiments, and we find that maybe pressure scale was an issue. So if you use a different pressure scale, you can bring the post-Spinel transformation nicely into the range where seismologists have seen the discontinuity. That's good, right? This is 2014, 3 years ago. This is our study. We study more pyrolite. We find a good match in laser-heated diamond cell. Now, multi-amble press community and our community start using the same pressure scale. They use the same scale, pyrolite. Yes, there are little differences in pyrolytic composition, but I don't think that could explain this discrepancy. Even the most recent literature, this was published in like 2010 or something, in multi-amble press, still gives you a lower pressure of post-Spinel transition compared to 660. Yeah, pressure scale is a real issue. It's not solved yet. And there could be some other effect that we have to worry about, which Abby can talk a lot about. And is that it? No. Post-perovskite transformation is another one. This is the post-perovskite boundary measured with different scale, MGSIO3. In an ideal world, we want to see all of them matching each other nicely. What do you see? Depends on which scale you pick. It goes down all the way to 105 GPa. It goes up all the way 130 GPa. It's still out there. So what are the problems? Well, there are many problems, but these studies use equation, pressure, temperature, thermal equation of state of standard materials like gold and platinum, where we don't know the electronic effect on thermal pressure very well. So people lump that effect into something, including myself, because we don't know theoretically very well. And that ended up resulting in some scary side effect of using these scales, as well as other experimental problems. Now, we try to understand this problem more fundamentally, so my group has worked on comparing gold, platinum, MgO pressure scales. They are standard materials. We thought we really know the equation of state very well. Fact of the matter is, we use the most recent pressure scale in the literature of all these three scales. And the baseline here shows the pressure obtained from magnesium oxide. Red ones are the gold, and the blue ones are the platinum. In an ideal world, you want to have 0, right? All the data lying, matching nicely between 3 different scales. It's like you have 3 rulers. You want to have them the same, right? If my daughter's ruler is longer than my son's ruler, right? It's not good. This is the curve for the gold. This is the curve for the platinum. So gap between them shows you mismatch between these scales. Don't ask me why this way. I don't know. But there's somebody out there who plays with us that the 660 is here. The gap is large there. And then magically gap close up. Post-perovskite transition is here. Gap is widening there. I have 0 idea what's going on.
But here, from the red to the blue curve at around 130 GPA, the difference is only 3 GPA, and yet in the previous plot, the difference was like 30 GPA.
Yeah, so there should be other effect. Yeah, it's not entirely equation of state. Yes. So for the seismologist and geodynamicist, this is about 3 GPA difference or 5 GPA difference. 5 GPA difference at the core boundary, 100 kilometers. 100 kilometers. Here, 60 kilometers. Can you allow the discontinuities at 600 kilometers rather than 660? Yes or no? Bridgmanite, I'm going to go quickly because I only have 5 minutes. So Bridgmanite can contain a bunch of other things like iron and aluminum. Can equation of state changes with this composition, right? There are some good literature out there. Fe2 plus, for example, doesn't seem to change the equation of state of Bridgmanite very much. It does change density, though, right? Because it changes the mass of the mineral. And Bridgmanite, if you think of Fe3 plus, aluminum 3 plus is controversial, but at least our group study shows it makes Bridgmanite more compressible, okay? But there are other groups that doesn't think that way. Okay, ferropericles, second most abundant phase in the lower mantle, famous for its clear spin transition. And this is how the spin transition influenced the equation of state of ferropericles. So at low pressure, if you're sticking in iron in ferropericles, because ionic radii of iron is bigger than magnesium, it expands the volume. So volume of iron-bearing one is always slightly higher. Okay? Following me? I know, it's tough, right? I promised you the break, but I couldn't. If you compress it, it runs almost parallel to the magnesium end member, which means that compressibility is similar. The volume gap is there. Now, if you look at this interval, volume of iron-bearing one approaches that of the magnesium end member, which means that when iron undergoes spin transition, the ionic radii of iron becomes very similar to that of magnesium. Okay? That's why volume, fancy word, collapses into magnesium end member. How dramatic is that, right? It doesn't collapse, but we love to, dramatize what we found. So now, simple question to ask. Bulk modulus, before and after spin transition, yes, it's probably the same as magnesium end member because bulk modulus is a slope in this plot. What happens in this interval where you have a spin transition? The slope steepens, right? It goes this way and rolls and then flattening again. Okay? Think about it. Then that should change the bulk modulus in that interval, like this way. A dip, right? So when you have a spin transition gap, ferropericles becomes anomalously compressible in that range and then comes back after spin transition. So it creates this funny dip in the bulk modulus profile in the lower mantle that translates into the same dip in bulk sound speed in the lower mantle. And if you throw that into the pyrolytic model, it still survives there. So if you take into account the spin transition happening in ferropericles and throw in that compressibility change in the pyrolytic model, unfortunately in the mid-mantle, you don't have a match between pyrolite and prime anymore. Okay? It varies with the content of iron in ferropericles. So it varies between like 1,000 kilometer to 2,000 kilometer. So
Dan,
it's highly
quick
dependent.
question is you're saying this portion of the mantle is not pyrolytic.
I don't know. Well, I have a paper that is under review right now that I propose how to solve this issue, but I don't have time to talk about it today. But there could be a solution. So now, lower mantle, we all think it's dry because you heard about physicists saying that you can now store proton in bridgmanite and ferropericlase, just about 50 ppm level. That's tiny, tiny. Wasdieite can contain 1 to 3 weight %. It's many orders of magnitude difference. But now you hear, have you heard about phase H? Yeah, so you guys are following literature, nice. Mineral physics literature. There's also the phase called delta ALOH. There are a bunch of other phases out there that are stable under lower mantle pressure conditions, likely close to geothermal temperature conditions. It turns out that those 3 or 4 newly discovered minerals all have structure related to stishovite. Okay? So this is a crystal structure model with hydrogen dangling in an interstitial void in a rutile structure or stishovite structure. Okay? Can those minerals are really stable under lower mantle? One way to check it is to use equation of state. And now this is different application of equation of state. So if you write down the Gibbs free energy, now there's a pressure term, which is most influential in deep mantle. So volume change. If you expand the volume, the system will hate it because it's going to increase the Gibbs free energy, makes it less stable, right? That's why you have phase transformation, because if you have a phase transformation, normally delta V becomes negative, and that decreases the delta G, and that gives you stabilization of new dense phase. So if you stick it in the hydrogen, in most cases, it actually expands the volume. So you actually work against the thermodynamics. So now we measure the volume of dry and wet stishovite. Yes, wet ones have larger volume than dry ones. Hydrogen expand the volume. But when you compress it, you see that it is more compressible and merges into dry ones. So now, if you want to put proton or OH into rutile at certain high pressure, you don't have to pay a Gibbs free energy tax anymore. Okay? You don't actually increase the free energy of the system. Now there's a very important application coming in for the exoplanet. I'm not going to go through, but all this exoplanet composition identification comes from knowing equation of state of different materials. Although the problem is if you go to extremely large planets, they have extremely high pressure, and then equation of state doesn't become really matter, and it's the mass of atoms that matters a lot. But for the Earth-sized planet, now they start seeing Earth-sized planet with their telescopes. Not visually, but through spectroscopy, another method. And for the Earth-sized planets or smaller size, which that they are more interested in than super Earth, equation of state really helps them to figure out the composition, bulk composition of planets. So I'll end there, I'm sorry. So those who wants to follow up with today's talk, I recommend 2 papers up there. The third one is shameless promotion of my own paper, but this deals with a little bit of tutorial. It's not theoretical. The first 2 ones are theoretical ones that you probably want to read. The third one, in case you want to do computational sort of like little tutorial stuff, the third one comes handy. Any questions? Or we are ready for coffee break. And I'm happy to answer questions during coffee break. Yeah.